So we wrapped up last video talking about independent and dependent events. And just to recap, that means that the probability does not get changed. The event's probability does not change when the other event happens. So the probability of B is still equal to the same exact thing when A occurs. The probability of B given that A occurs is still equal to the probability of B. And vice versa. Probability of A doesn't change when B occurs. So seeing an example of that to actually prove it, you would want to get those numbers and make sure they're equal to each other. So here's a situation, getting the flu and being a man or a woman. So the flu is pretty indiscriminatory. It gets men and women pretty equally. So you would think these are independent events. The probability of the flu is going to be the same whether you're a woman or not. So let's just look what we have from the table. What's the probability that you randomly select somebody and it's a woman? Well, there's 521, women. There's 1,250 total women out of the total number of people in our study. So for this study, there was this probability of being a woman. What's the probability you get somebody that has the flu? This many people had the flu out of the total. So that's how you get the probability that someone has the flu. So given that we randomly select that the randomly selected person is a woman, so if we're only looking at the woman category here, copy that. If we're only looking at the woman category, we're given that. What's the probability that they have the flu? Not they the flu, but what's the probability they have the flu? So it'd be 250 out of the total. And so you see that's the same probability of having the flu out of everybody in general. So we've proven independence there. The probability of having the flu does not change whether it's everybody or whether you know that it's a woman. And just to verify, it should work vice versa. Given that a randomly selected person has the flu, so if we're only looking at people with the flu, we're only looking at that top row, what's the probability they are a woman? So that is 250 people out of the 521 that are women. And you see that's the same probability as being a woman overall for this population we have. So these events are independent, and we proved it by showing those probabilities are equal. So now to look at the multiplication rule, it's the probability that two events, and we're going to call them A and B, will occur in sequence. And we read it, it's the probability of A and B. And how you calculate it is you do the probability of A, the first event, and multiply it by the probability of B, the second event, and you have to use the conditional probability of B because A has occurred. So if A occurring affects the probability of B, you multiply by that new affected probability of B. If the events are independent, like what we just looked at with the flu in women, any independent events, when A occurs, it doesn't change the probability of B. So then you can just multiply by the probability of each event and not worry about calculating the conditional probability. So let's look at an example of this here. If we want to find the probability of flipping a coin and getting heads, then heads, then heads, so heads 3 times in a row, you just multiply the probability of each event together. So the first time flipping a coin getting heads, it's 50% chance. These are independent events. Each coin flip still has a 50% chance. So it's going to be 50% again, and the third coin flip is still 50%. So the probability, just multiply 0.5 times 0.5 times 0.5, and that gives you your probability of getting heads, then heads, then heads. Now, what's the probability of drawing 3 queens in a row from a deck? Well, the first time you draw, there's 4 out of 52 that are a queen. So that's your chances of getting a queen on the first draw. Now, the probability of getting a queen has actually changed on the second draw. So this is conditional probability. Now there's only 3 queens left, and there's only 51 cards left. So the probability of getting a queen has changed. And on the third draw, now there's 2 queens left and only 50 cards. So we get that probability. So let me drag this down here. If we multiply those 3 probabilities together, we get the probability of drawing a queen, then a queen, then a queen. So that's our multiplication rule. Just multiply the probability of each event together But be careful, if the probability has changed because one of the previous events changes the probability of the next event, you have to use conditional probability. Let's look at a couple questions that you could ask with this. Let's say the probability of getting the flu is 20%. What's the chances that you randomly pick 6 people and they all have the flu? So the chances of getting the flu is 20%, regardless whether somebody else has it. So the probability for each person is still 20%. So we just need to multiply 20% together, 0.2, 6 times. And this will give us the probability here that all 6 have the flu. Now, what's the probability that none of them have the flu? Well, if you think about that, if there's a 20% chance of having the flu, then that means there's a 1 minus 20% or 80% chance that you don't have the flu. All right, 20% chance you get the flu, 80% chance you don't. So the chances that nobody out of the 6 has the flu would be 0.8 now multiplied by itself 6 times, or to the 6th power. Put an equal sign in front of that. And there's our calculations for the probability that none of them have the flu. What's the probability that at least one of them has the flu? At least one has the flu. So if we're trying to find at least one person having the flu, we think about the possible answers you could get if you asked 6 people whether they had the flu or not. It could be 0 of them have it, 1 person could have it, 2 people could have it, all the way up to 6. So these are your only possibilities. And these are all the possible outcomes, so they all have to add up to 1 or 100%. And so we know the probability of 0. We just calculated that. The probability of 0 is right here. It's 0.8 to the 6th power. That's the probability that none of them have the flu. Well, the rest of these have to contribute to add up to 100%. So if we do 1 minus that answer, we get what all of these together must add up to, and that's the complement. So we talked about that with probabilities. If the probability of 0 is this, the probability of its complement, which is at least one person having the flu, must add up to 1 when you put those two together. So 1 minus the probability of 0 is the probability of the complement, which is at least one person having the flu. The next definition is mutually exclusive, and that's when events cannot occur at the same time. It's impossible. So, for example, having the flu and not having the flu, that can't happen at the same time. Or the Patriots winning the Super Bowl and the Eagles winning the Super Bowl. They can't both happen at the same time. It has to be one or the other. So if they can't happen at the same time, they're mutually exclusive. That means there's absolutely no overlap. So if this picture right here is trying to indicate that there's absolutely no overlap between the two events. Everything that could happen to make the first event true is here, and the second event is completely separate from that. And this picture is illustrating that there is some overlap. There's some times when both the events are happening at the same time. So for example, A could be being a woman, and B could be having the flu. So this B circle contains everybody that has the flu, and then there is a portion of that are women. So there are some overlap here where you're in both groups at the same time. So those are not mutually exclusive because they can both happen at the same time. And we introduced mutually exclusive so that we can talk about the addition rule. And it's just saying, what's the chances that we get one option or the other, either A or B occurring? If either one happens, we'll be happy. What's the chances of getting either one of them? And the most fundamental way to calculate that is when they are mutually exclusive events, we just add up the probability of A and add the probability of B. So add the two together and you get the probability of A or B. So maybe an example of that, rolling a dice, what's the chances that you get either a 4 or a 5? Well, the chances of a 4 is 1/6. The chances of a 5 is 1/6. So just add those together. The chances you get a 4 or a 5 is 2 out of 6. And that makes sense. That's 2 out of the total 6 numbers. So it's a 2/6 chance of getting a 4 or a 5. Now if the events are not mutually exclusive, you have to do a little bit extra. You have to subtract the probability that you're getting both things at the same time. So in a sense, that part in the middle, that where A and B can both happen at the same time in the middle of the Venn diagram here, that's being counted here for the probability of A. It's being counted again for the probability of B. So it's got counted twice. You just need to subtract it away to get the probability of A or B. So let's say you're playing a dice game and you're going to win if you roll something less than 3 or odd. So some weird game, but that's how you win. You have to roll a less than 3 or an odd and you're going to be the winner. So let's just add those probabilities together. What's the probability of rolling something less than 3? That's either getting to 2 or a 1. So you have a 2/6 chance of that. What's the probability of getting an odd number? Well, that's a 1, a 3, or a 5. So that's 3 out of 6. So we're going to add those together, but we need to subtract the probability that got counted twice. And that's because the number 1 is in both groups. So we're going to have to subtract away 1, the 1/6 chance, because there's one number there out of the 6. So if we added those together and subtracted the probability that we're meeting both criteria, we get 4 out of 6. And so we can reduce that to 2/3 or as a decimal. An example here from the book, what's the probability that someone has type O or type A blood? You can't have both at the same time, so we got mutually exclusive. We're just going to add the probability of having type O, which is 184 out of the total number of people, and the probability of having type A, 164 out of the total. And if you add those together, you get the probability of A or O. Now the second question, find the probability that the donor has type B or is Rh negative. Now you can be both there. So type B blood would be 45 out of the 409. So we're going to add that. Let's see if I can get it to show. There we go. 45 out of the 409. Probability of being Rh negative is 65 out of the 409. And then we have to subtract the probability of being both. So if you look up here, the probability of type B and negative, that's 8 people out of the total. 8 out of the entire 409 were in both. So that's the probability of being both. So we're going to have to then subtract that probability that you meet both criteria, and that's how you get the final answer.